we're going to hear from Fulvio Sinisi, who graduated in material sciences at the Padua University in 2016. He then was hired at LEGO. He's the R&D and technical support manager of the plating division unit. He deals with identifying solutions for electroplating, enhancement of the already existing project, and developing customized solutions. He always provides technical support to the marketing area of the plating division, devoting himself to different accounts worldwide. The title of his presentation is Steel in Jewelry, Superficial Treatment that are nickel-free. As of late, steel has been used in jewelry, which is a more economic alternative to more precious alloys that are usually used for jewels. We're now going to be hearing about the state-of-the-art of electrodeposition on steel, together with a case study on the optimization of electrodeposition to reduce at best, if not eliminating, the nickel release by treated alloy containing steel. I'd like to remind you that we're going to take your questions at the end of the morning session, so please, you're kindly invited to fill up the forms that you've been given in the folder, where you can put down your questions, and the questions shall be addressed to the individual speakers by myself. So should you have any requests, feel free to voice your questions or to fill the form and let us know what your questions are. Thank you. Thank you very much. Good morning to you all. In today's presentation, we shall shed some light on stainless steel alloys, trying to understand what the main features are that led to the dissemination of this alloy even in the jewelry industry and for fashion accessories. We shall look at the analergic main feature of this alloy, despite the small content of nickels. Then we are going to have a look at the superficial treatment of stainless steel by means of electric deposition. And then we're going to look at the nickel-free electric deposition on stainless steel, looking at 3 case studies. Over the past few years, fast fashion has put forward a demand for high durability and low-cost jewels, so much so that new materials have been identified over and above precious metals for the production of fashion accessories and jewels, and this is the case for stainless steel and titanium-based alloys. The stainless steel jewels took up at the beginning of the 80s. The first industry is that are watches. Indeed, stainless steel is actually an alternative to the manufacturing of watches. The reasons why stainless steel has been used in the fashion industry and jewelry is connected to the low cost and availability of this material. Then it is highly durable, it has a scratch resistance, it has good resistance to corrosion, and it is easily found. Stainless steel is also recyclable. Finding the raw materials to develop stainless steel is not very complex, neither is it costly. Most stainless steel alloys do contain nickel, yet these alloys may be considered as nickel-free in that they don't elicit any allergic reaction. On the other side, we can also say that it is not to be considered an investment because the material is a low-cost material and you cannot obviously expect an increase in the value. Hardness could be considered as a disadvantage because they tend to be difficult to polish and to reshape it. On top of that, stainless steel alloys usually have a low chemical inertia, so much so that they can be easily attacked by chemical materials, by chlorides, seawater, or bleach, and other such materials can tarnish it. It does contain nickel, though in a very little percentage. So the stainless steel alloy is a special steel. It contains carbon and iron, carbon to a maximum of 2%. It is considered stainless when chromium is added in a percentage which shouldn't be higher than 10.5%. Chromium allows for oxide being generated that actually makes the alloy self-passivating. So this coating, this layer of oxide, makes it less vulnerable to corrosion, and it is a barrier against the migration of the elements that are included in the alloy. Nickel, first and foremost. Nickel is actually included in all stainless steel with a percentage of up to 10%. It makes the alloy homogeneous, and it makes the alloy enjoy certain features such as resilience and flexibility. Other elements can be contained in lower percentages, not over 5%, granting certain additional features, for example, resistance to corrosion or hardness or other mechanical properties. There are stainless steel alloys that are nickel-free. Nickel is indeed replaced by manganese and nitrogen, but to date the performance are not satisfactory. The classification and the nomenclature of stainless steel is included in the UNI norm 188, which includes again the specifics for all the steel alloys. Actually, they can be classified based on the chemical composition or to the mechanical performance. When it comes to fashion and jewelry, steels are usually known based on their AISI coding system with a 5-digit and a letter. L, for example, stands for low carbon content as a feature of that alloy. Here you see the stainless steel alloys that are most widely used in jewelry and fashion. The ones that you see in bold letters account for some 90% of the production of fashion and jewel items. AISI 304 is the one that has a good property against corrosion. Then 316 is even better, but it costs more, and it includes more nickel. Nickel is a very important component in the alloy. Indeed, we know that allergy to nickel is one of the more easily found. Indeed, most people suffer from it. This is why there's a very strict regulation on the release of nickel through these nickel-containing alloys. So necklace and bracelets and rings should not include more than 0.5%. In the case of earrings, for example, the percentage of nickel should be even lower. So if the rules are complied with, so if the nickel percentage is lower than that set by the norms, you can actually talk about a nickel-safe object. And nickel tested implies that it is a super safe object that has been again tested. Sometimes you can also read nickel-free in the stainless steel alloy, and this is not totally true, because nickel-free should actually contain no nickel at all. But as a matter of fact, nickel-free may be used also for something that contains some nickel, and it is in fact nickel-safe in that no allergy is generated. The release of nickel by means of item of jewelry should comply with two regulations: 211 for jewelry and fashion items, and in eyewear there's another standard. In the case of any object with some superficial coating, and abrasion should be carried out to see what happens afterwards. The two regulations are different. And to measure the nickel release, artificial sweat is used on the surface. A test is performed between the object to be analyzed, the surface to be analyzed, and artificial sweat solution. With 2011, the object is totally included in the solution. In the case of eyewear, there's a band which is containing artificial sweat, which is connected to the item of eyewear. The test lasts for a week. The temperature is of some 30 degrees. At the end of the test, the nickel presence is detected. Stainless steel alloys, as listed here in this slide, can be considered as an allergic because the nickel release is compatible with the regulations. And we will be referring to the regulation, to the alloy as such. At times, this alloy is not enough. Additional treatment added on the surface to modify the properties, for example, the aesthetic properties, to change the color of the jewel or the fashion accessory, or to improve corrosion resistance. In the case of the fashion industry and jewelry, superficial treatment should exclude paints, especially so in the watches, because the outlook can be worsened. PUD is an acronym that stands for PVD stands for physical vapor deposition. It includes the evaporation and condensation of a solid source, which is often defined as target. There are many techniques to be used for PVD, depending on the type the metal is evaporated. In jewelry, usually it resorts to arc evaporation. An arc discharge is triggered between the target and the walls of the deposition chamber. Discharge with a current of the order of some 50-100 ampere is localized over a limited region of the target surface. There's also the sputtering can be used. A high-energy ion beam bombards the target, detaching atoms or molecules that move into the chamber and condense on the substrate. Both technologies include the transport and recondensation of the vapors emitted by the target. Nowadays, technologies include high energy ion that produce vaporization. This is called, again, ion plating technology, that allow for the transportation of vapor so as to make the development to the coating as homogeneous as possible. PVD includes a pre-treatment of the sample. As is the case of any electroplating, you have to do away with impurities so as to improve the adhesion of the vaporized materials on the substrate. So the sample is then placed on basket in the deposition chambers. The baskets are oriented so as to promote the adhesion of the coating. Vacuum is generated with pressure equal to 10 at -5 and 10 -7 millibar. The target is transformed into vapor, and the metals are then deposited on the substrate. Afterwards, the chamber is cooled down. With these systems, at times you can have reactions with the deposition of the metal together with gas, which is not inert but reactive, as in the case of nitrogen, oxygen, or acetylene. You might create on the substrate carbides of the metal included in the target. The temperature ranges between 100 and 1000 degrees, depending on the type of target, on the type of process required. And 3-6 micron per hour are then added on the substrate. This technology can only be used for certain materials, those that are extremely strong, such as tungsten, copper, and stainless steel. Deposition can also be performed on magnetic materials, ceramic and glass, but it is more difficult. Other materials, such as brass, alpaca, aluminum, and sinterized materials, require a pretreatment. Oftentimes, electrodeposition is resorted to before, in the case of low melting alloys, they cannot be treated with PVD treatment. In the case of zinc tin alloys, or those with a soldering, including some of the elements that I've just quoted. Coating by means of PVD includes titanium, zirconium, and chromium, which interacting with inert gas can create the pure metal, or there could be oxides and the carbides of the above-mentioned materials be generated. The colors that are usually resorted to in the jewelry and fashion industries are the ones that simulate gold, and those are obtained by means of deposition of titanium nitrides that look more like 24 karat gold. Carbon nitride are often used to obtain other colors different from the ones that you may obtain with other technology. For example, bluish coloring, or the famous rainbow effect that you see at the bottom of the slide on the left. PVD technology grants one major advantage in that depositions coating can be obtained that have a high resistance to corrosion and wear. It is a very slow process. You may control the deposition layer upon layer. And no toxic metals are used, so all the metals that are used are kind of green, but no nickel is ever included. Different colorings can be obtained that are quite specific to the use of this technology. No byproduct, no toxic byproduct is generated. This process can be used not on all materials. You cannot have large size manufacturing because you have to fill in the chamber, and it is a very time-consuming process. Usually electrodeposition develops micron by the minute, and this is a much slower process. With complex shapes and hollow items, this is very difficult to use. It requires very costly equipment, so you have to have important investments, and you have to train your staff. Electrodeposition is known to all and everybody. You can have a deposition of a metal of an alloy by means of an electrolytical process. As you see here in the slide, you have a generation of voltage using different potential. You can generate continuous currents by means of which a number of chemical reactions are promoted with redox reaction, so that the metal ion included in the electrolytical solutions are deposited on an electrode, which is a cathode, i.e. the object to be coated. Oxidization is obtained at the anode. It could be an oxidization that involves also the melting of the anode in the case of soluble anode, as is the silvering process, silver deposition process. So you have metal and another substances that are used on the cathode. That is the object to be coated, and that grants specific features to the electrodeposition, either physical or aesthetic features. Electrodeposition is the technique which is more often used in the field of jewelry and fashion items. Indeed, any type of metal can be used, which is often required in the fashion and jewelry industries. You can combine different elements so as to fine-tuning the different coloring. So you can obtain light color gold or 24-karat gold, or you can have warmer colors or reddish colors, adding copper, for example, to the alloy. So to have a white coloring, you can use platinum, rhodium, and black can be obtained by means of electrodeposition of rhodium and ruthenium bound up with other chemical substances or blackening items that combine with the metal so as to obtain this black coloring. Electrodeposition has a number of advantages. It doesn't entail very high cost materials. This is a fast treatment, a micron per minute. Precious metals that are used can be recycled. Different metals can be used to obtain different colorings. You cannot have in situ deposition as with PVD process. The cost of the raw material is different, of course, depending on what you want to use. So one of the main defect is that chemical solutions are added, at times even poisonous substances such as cyanide. So the disposal of this material is kind of risky and difficult. Considering the advantages and disadvantages of the two technologies, PVD technology is considered being as the one which grants best compatibility with stainless steel. And it is actually the first option with stainless steel. This doesn't mean that you cannot have electrodeposition on stainless steel. The only limitation is that you have to dispose of the chromium oxide. With electrolytic deposition, you have to have conductive substances. The presence of an oxide is indeed an obstacle that can be solved by means of scratching the material and preparing the surface before the treatment. Usually different layer of nickels are used. And this is why, at the beginning, we tended not to resort to electrodeposition in the case of the fashion and jewelry industries, because nickel will be added, thus creating problems in terms of the release of nickel. Nickel-free cycles for stainless steel objects have been developed. You just have to remove the nickel deposition, usually replacing it with gold deposition. What is difficult is making sure that the analergic feature is maintained. When you scratch the chromium oxide on the surface, sometimes you also remove the barrier that you have in stainless steel, safeguarding the object from releasing nickel. So by means of nickel-free electrodeposition, you have to remake this barrier effect so as to contain the potential release of nickel. This is a project that we've carried out at LEGO, where electrodeposition was performed on screws to be used in eyewear using 316L stainless steels. The release is compatible with the rules. The same screw that was subjected to electrodeposition was releasing nickel 5 times more as included in the regulation. So the barrier was not sufficient. This is why subsequent studies were carried out within LEGO to develop nickel-free electrodeposition cycles whose objective was that of reducing the nickel release after electrodeposition. In this study, the request that had been put forward by a client in the eyewear industry was very complex. Within the same eye, within the same glasses, there were copper alloys and stainless steel, and basically you have to prepare the surface for that purpose. Before the project was carried out in Legor, the client was too much focused on copper. At the beginning of the cycle, nickel was used, nickel wood, which is a chloride nickel, and then nickel deposition was often resorted to make the object resistant to corrosion, but the barrier effect, preventing the release of nickel after electric deposition, was only relying on the spray cycle. 12% of the production failed the test in terms of nickel release, and the samples with a smaller release were very close to the threshold limit, if not exceeding that limit. And those would be accepted because the regulation allows for higher percentages of nickel being released. It is not too restrictive. At Legor, our first study was a set of studies were carried out, analyzing 3 electrodeposition cycles. The activation of the surface was a common feature, and that was based on a treatment based on chlorhydric acid. In the first cycle, nickel wood was still used, whereas in the other 2 cycles, gold plating with an acidic layer was resorted to. The nickel was done away with. Then the final depositions were palladium nickel, 80-20 alloy, which is a certified alloy, with nickel release that can play with the rules, well under the threshold limits, and a painting layer. In the first cycle, we wanted to make sure that the release of nickel was only due to the nickel layering, or if the underneath metal was releasing nickel. In the cycle 2, we use palladium. In cycle 3, we only use a nickel-free, and it was palladium iron that were used. Performing the release test, we saw that cycle 2 and 3 were granting best results. This meaning that nickel wood did contribute to the release of nickel. The cycle number 2 is the one that was tested because it was more similar to the cycle that we resorted to earlier on with palladium nickel. 100 samples, 100 item of eyewear was released. The treatment was carried out with chlorhydric acid because there was a bronze alloy. The frame of the spectacles were tested. The release test was approved with the problems of the customer being solved. The client basically was happy with our project. It has entrusted Legor with the identification of an electrodeposition process leading to thick layers, 5 micron of a precious metal electrodeposition. The initial cycle is the one that you see depicted here in the slide. Nickel was detected in the electrodeposition cycle. The surface was not activated at best. Another critical issue that you can see quite easily with this electron microscopy image showed that with this thick electrodeposition layers could cause problems because adhesion between the different layers might be failing, or there could be cracks that might not be visible. Such cracks, therefore, can lead to the migration of nickel from the object to the wearer. The nickel included both in the stainless steel alloy and the releases in this case were unacceptable. Legor has come up with a proposal including 2 different cycles. These cycles have been developed in the manufacturing process. Nickel was totally done away with, so the adhesion with the surface had been obtained through a very acidic gold plating. Acidic copper was added, and the layers of precious metals have been carried out using, again, the gold plating. The gold plating has been done with 18-karat gold plating, for most of the gold being layered, and a 23-karat gold additional layer to make a more effective barrier, and an alkaline addition to get to the color that the customer was requesting. IEC 316 was used, and treatment has been used with chlorides and acidic substances. The test performed showed that the release amounts of nickel are well below the threshold limits, less than 0.5. Both the electrodeposition cycles were effective. Now we're using cycle 2 because they're the one that requires the least amount of 23-karat gold. In this last case study, the request that was put to us to a customer making bracelets asked us to support him in the electrodeposition of the spring with IEC 301 stainless steel. The main feature was that IEC 301 releases 1.4 micrograms, so the release was not compliant. This type of stainless steel basically was leading to too high a release. The client requested a 0.2, despite the regulation being more tolerant. And the precious metal shouldn't be bigger than 2 microns and shouldn't require any painting. 2 cycles have been tested in the lab. The activation of the surface was similar to the ones that we've seen earlier on, and the adhesion was promoted with the acidic gold plating. The new item is white bronze layering. These white bronze usually include a cyanide, and in the field of eyewear, they are not well tolerated. In this case, this is an accessory we're talking about, so we didn't have any problem using cyanide. The difference between cycle 1 and cycle 2 is that cycle 2 doesn't include acidic copper. White bronze was deposited on the gold layer. It is fully nickel-free. It is a palladium with iron. Acidic gold with 23-karat gold was used, adding an additional substance to obtain the color that was requested. With cycle 1, the release of nickel was below the threshold limit, and cycle 1 actually is a good solution. Cycle 2 yielded releases over the one that are tolerated. There was too thick a deposit, Probably the deposit was not correctly carried out after bronze. Probably there is a lack of compatibility in having white bronze on top of a gold plating that was fully acidic. Cycle 1 provided us with a good solution, and over the next few weeks, a beta test is going to be performed using, again, cycle 1. My presentation is over. Thank you very much for your kind attention.